Today we're going to take a look at section 12.2, which is differentiation and integration, obviously on vector valued functions, since that's what our whole chapter 12 is about. And we're going to start with a definition. And the first definition is going to relate to differentiation. So the derivative of a vector valued function R of t is r prime of t equals the limit as delta t approaches 0 of r of t plus delta t minus r of t over delta t. This is true for all t for which the limit exists. If r of t I think that's to say r prime of t, there we go, exists, then r is differentiable at t if r prime of t exists for all t in some interval I, then r is differentiable on I. All right, and more practically speaking, in terms of, computationally, Theorem 12.1 says the following. If r of t is equal to f of ti plus g of t j plus h of t k, where f, g, and h are differentiable functions of t, then r prime of t equals f prime of t I plus g prime of t j plus h prime of t k. All right, so component-wise differentiation, right? That's what we're doing. So we're going to do some examples with some derivatives now. I think I've space enough for this one on this one. So our first example is to find the derivative. We're going to do the derivative of r of t equals e to the t squared e to the 2t, and secant of 2t. Okay, so in doing r prime of t, we'll take the derivative component-wise. So the derivative of e to the t squared would be a chain rule. The derivative of t squared is 2t, and the derivative of the e to the power is e to the power. T squared e to the 2t would be a product rule, so we'll do the first times the derivative of the second, so the derivative of e to the 2t would be e to the 2t times 2. So we'll move this over and put the 2 in front. Okay, and then on the second component of that, plus the derivative of the first piece, which would be 2t times the second. All right, and then the derivative of secant 2t. So the derivative of secant t would normally be secant tangent, so the derivative of secant 2t would be 2 secant 2t tangent 2t. Okay, so we're going to do another one, direction slightly different. On this one, example number 2, we're going to find several things. We're going to find first r prime of t, and then r double prime of t. So you'll notice I didn't define that. Again, that's because it's exactly what you would expect it to be. For c, we're going to actually take the dot product of those quantities, so r prime of t dot r double prime of t. And then finally, we're going to take the cross product of those, so r prime of t cross r double prime of t. And we need an r function for that to happen. So this is for r of t equaling 1/2 t squared I minus tj plus 1/6 t cubed k. All right, so our first one is a first derivative. So 1/2 t squared would be 1/2 times 2t, or just t, I. Minus tj would be minus 1j. I'll put the 1 for now. And then 1/6 times 3 would be 1/2 t squared k. So that's A. B is the second derivative. Okay, so with the derivative of the derivative, so this becomes just 1i, or I. This becomes actually plus 0j. I'm just going to write it in because it'll be able to help us later on in the problem for the next parts. If you don't want to write it in, that's fine. And then the last one, the 1/2 times the 2, would end up making this just tk. So on part C, we're going to do the dot product of these two vectors. Okay, so if you remember the dot product, we're going to take these component-wise and multiply, so t times 1 plus negative 1 times 0 plus 1/2 t squared times t. Middle term obviously goes away, but otherwise I end up with a t at the beginning plus 1/2 t cubed at the end. Okay, and of course the one that's the most work is the cross product. So for my cross product, I need the component-wise, or not component-wise, but the determinants of each of these. So for I, it would be negative 1, 1/2 t squared, 0t times I, minus, and then I need t, 1/2 t squared, 1 and t, good, and that's j, plus, and then I need k components. So for k, I would have t, negative 1, 1, 0, and that's k. All right, so working through it piecewise, we would do our diagonals. This ends me up on the first piece with negative ti. And then I'd have t squared right here, minus 1/2 t squared, so that would be 1/2 t squared. But then I have the minus in front here, so this is minus 1/2 t squared, j. And then along my other diagonal, this one's 0. This piece right here would be -1, so it's subtracting a -1, which would be +1. So plus 1k or just plus k. All right, so anytime we talk about derivatives, you would kind of want to also talk about smoothness, continuity, those kinds of issues. So we're going to move into that direction. I have space on this one, I think. Yeah, for a note. So this is a definition. We say a curve traced out by the vector valued function R of t equals f of t, g of t, h of t is smooth on an interval I if R prime is continuous. On I and R prime of t does not equal 0. Except possibly at the endpoints of I. All right, so we're going to determine if our next function is smooth. So determine if the given curve traced out by R prime of, or R of t, not R prime, R of t is smooth. And R of t is going to equal t to the 4th minus 2t squared. And then I've got 2t squared minus 2t. So we're looking at a planar vector in this one. All right, so to start, this is continuous. And a reason, of course, is because f of t and g of t are polynomials. Okay, so next we're going to find out if, in fact, this equals 0 anywhere. So if I just take the derivative of it, if I take the derivative, I have 4t cubed minus, let's see, 4t, and then 2t minus 2. And the question is, does this ever equal 0, 0? So we have two possibilities, right, that we had to look at. 4t cubed minus 4t equals 0, and 2t minus 2 equals 0. Of course, the second one is easier to solve. I add the 2, I divide by 2, and I find that t is equal to 1. So the question is at t equal to 1, does the other function also equal 0? Because it equals 0 at 0, too, but the second one didn't. So, in fact, this one right here, if I were to solve it, I have 4t squared, which would then be t minus 1, I wrote that wrong, I'm sorry, for t, there we go, and I have t squared minus 1 equals 0, so that's going to happen at t equal to 0, 1, and negative 1. But the part that matters is the one that matches. This is t equal to 1, and this is t equal to 1 in here. So this is going to be smooth. At, or it will say for all t on I, t not equal to 1. Or if you wanted to write it in interval notation, negative infinity to 1, 1 to infinity. All right, so we're going to switch gears and look at integration now. So for the vector valued function, r of t equals f of t, g of t, h of t. The indefinite integral of r of t on a, b, I'm sorry, that's not supposed to be there, that's for definite integrals, this is for indefinite integrals, that's the word I want, is. So r of t, capital R of t, is the integral of f of t, g of t, h of t, dt. And honestly, that's the integral of each of these individually. So just like with the other notations, that becomes, it becomes the derivative notation here of f of t dt. We're sort of interspersing the information to each function specifically. But the cool thing is that that actually ends up being a capital F, capital G, capital H, if you want to think about it that way. This is f of g, f of x, g of x, there's my g, and h of x that you're looking for. Okay, so let's do an example. We're going to find the indefinite integral and we're looking at the integral of 2t minus 1 I plus 4t cubed j plus 3 square root of 2k dt. Okay, so taking antiderivative, this would become t squared plus t plus some coefficient k, so I'm going to call it k1 I, plus 4t cubed becomes t to the 4th. And then I need to add a limit of integration, right? k2. That's times j plus. Now, 3 square root of t is what this would say, not 2. Sorry about that. 3 square root of t would be t to the 1/2, so we increase the t to the 3/2. And then if I divide by 3/2, 3 divided by 3/2 is 2. And that's k. So that is our antiderivative. Oops, I forgot one piece. I'm so sorry. Right here. I should have said plus k3. And of course that k at the end is the unit vector in the z direction, not the k that's in the problem and the other components. Now I don't have a definition actually written down for what happens when we have a definite integral. This one was an indefinite, right? So if it were definite, it would mean that I would be working on an interval AB, and it would mean that as I'm working with this, there's A's and B's, all of these right here, and so forth all the way down. Okay, so that's the only difference between indefinite and definite integrals computationally. So let's actually find a definite integral now. So we're going to evaluate the definite integral. All right, and we're going to do this from 0 to pi halves. Our vector valued function is a cosine t I plus a sine t j plus k dt. All right, so first just antiderivative. The derivative of antiderivative of cosine is sine, so this is a sine of t I plus the derivative of a sine t would actually be negative a cosine t j plus t k. And evaluate from pi over 2 down to 0. Okay, so at pi over 2, I have a sine of pi over 2 minus a sine of 0. Well, a sine of 0 is 0. A sine of pi over 2 is actually equal to 1. So this would be a times 1 minus a times 0, if you will, I. I'll simplify it in a minute, but just so that I've written it down. So cosine of pi over 2 is actually 0, so this would be a times 0 minus, and then cosine of pi over, or cosine of 0 is 1, so this is a times 1, and then of course this is j, and then plus, and the antiderivative of t would be 1/2 t squared. Oh, I'm sorry. I'm about to take another antiderivative. That's not what I'm trying to evaluate. Okay, so pi over 2 minus 0, and that's k. There we go. Okie dokie, and simplifying, I end up getting that this is ai minus, or plus rather, aj, and plus pi halves k. And this would be my definite integrals vector. Right, one last question for this lesson today. And I've got a homework assignment for you on number 6. We're going to do an initial value problem. So find r of t that satisfies the initial condition. Okay, and my r prime of t that I'm starting with is actually 4e to the 2t I plus 3e to the t j. And I'm told that r of 0 equals 2i. Okay, so antiderivative first, right? So let's do the antiderivative with our components. So the antiderivative of e to the 2t would be e to the 2t, but then divided by 2. So the 4 will be divided by 2, so this becomes 2e to the 2t. And then you need plus k1. Or use a different letter if you don't like that one. This was I. And then we have plus the antiderivative of 3e to the t is still 3e to the t. So it's 3e to the t j, plus k2, right, plus the constant j. Okay, and we want to set this equal, or not equal rather, but we want to evaluate it at r prime, or r of 0 equals 2i. So this would be r of 0 equals 2 plus k1 I plus 3 plus k2 j, and it's supposed to equal 2i. There it is. Sorry about that. 2i. Okay, so this piece right here needs to be equal to 2, which means that k1 is 0. And this piece needs to be equal to 0, which means that k2 is negative 3. So we're ready to finish our vector. This is r of t equals 2e to the 2t I plus 3e to the t minus 3. And that would be j. All right, homework for this section. Well, you'll notice that WebAssigns have already been assigned. Because I'm getting a late start on getting this posted, I actually made it due on Monday, so you have a few days to work on it. The homework, and I do mean Monday of Thanksgiving week. We won't be in class, but you'll have a WebAssign due. I don't want you waiting until the Sunday before we come back together to do everything, so I'm trying to space it out a little bit. So this is page 810. I'm sorry, page 830. It's numbers 8, 10, 13, 22, 23, 26, and 27. 30, 37, 45, 48, 52, 55, 58, and 61.